Good evening, engineers. In fact, in this video, I would like to present um, the main changes of ACI 318.25 in Chapter 22. Okay, let's start. In fact, this table includes the main chapters that I have discussed before in my course. Unfortunately, that course was in Arabic, but I will try in the future to make one in English. This is something related to the frame design. Okay, let's start here. First of all, let's open the code. In fact, I would like to open the code uh, quickly. Okay. If you look here, if you look to the table of contents, you will find that the new organization of the code depends on the load transfer path. So here we have loads. The loads will be applied to the slabs, then will be transferred to then the loads will transfer to beams, then columns and walls. This is diaphragm also will transfer the seismic forces. Then finally we will go to the foundation. Here also we have connections, beam, column, and slab joints. Here, chapter 22, uh, uh, which is the main topic of today's video. If you look here, chapter, in fact, 21, 22, 23, 24, I'm calling, or the ACI calls these chapters as a toolbox chapters. Toolbox chapters mean that when you design any element, let's say one-way slabs, two-way slabs, or beams, you will go to the toolbox chapters to get some informations, and again you have to go back to the same chapter under consideration. So if we open, for example, if you would like to design a beam, let's say, so we will go to chapter 9. Chapter 9 is for designing the beams, okay? Okay. If you would like to calculate the required strength, let's say, I will see here. Okay. For example, if you would like to calculate the shear strength of the beam, the code will send you for chapter 22. Section especially 22.5. Chapter 22 is called sectional strength. That's why you will go to chapter 22, you will calculate the strength, the shear strength of the beam, then again you have to come back to chapter 9 for uh, continue or to continue to design this beam. Again, if you would like to design the beam for torsion, the code will send you again to chapter 22, but section 7 to compute the torsional strength of that beam. And again, you have to come back to this chapter. That's why we are calling those chapters as a toolbox chapters. Okay. So chapter 21 for strength reduction factors, 22 sectional strength, 24 serviceability requirements, 25 reinforcement details. So instead of repeating the requirements of shear strength to way shear strength, the code collected all these requirements in 4 chapters, and we are calling these 4 chapters as a toolbox chapters. The code will send you from a specific chapter to a toolbox chapters to get some informations, and again you have to go back to that chapter. In fact, chapter 22, the name of chapter 22 is sectional strength, referenced in member chapters by section. Used as a reference for strength calculations. From this chapter, you will find, or you can calculate the one-way shear strength, two-way shear strength, also torsional strength, also the interaction between the axial force and moment. This is required to compute the strength for columns, for example. Not intended to be read from beginning to end. Why? Again, because if you would like to design a column, the code will send you from chapter 10, which is for column, to chapter 22 to get some information, specific information. No need to read the all provisions of the tool box chapters. Only you will read some specific informations that the code will guide you for these informations or for these provisions directly. The scope of chapter 22 again, we can calculate the flexural strength. This is important for beams. Also axial strength, I need the pointer. Okay, axial strength or combined flexural and axial strength. This is important to find or to determine the sectional strength for columns. Also, we can calculate one-way shear strength, two-way shear strength, also torsional strength, also bear strength, also shear friction calculations, especially at the construction joints or for the frame design. So as you can see, these items, or I will say these sections can serve all other members, same like columns, beams, slabs, and so on. Okay, first of all, if you see this bar means that here we have an update or some revision in this provision. Some of these revisions are minor and some of them are major. Anyway, here you have to know that sectional analysis using linear distribution of a strain can be used for a normal conventional beams, but if you have a deep beam, as per ACI code, you have to use strut and tie analysis. The definition of deep beam can be found in section 9.9 in ACI code. Also here we can see that in ACI 25, the code provided a simplification assumption for calculating the effective depth for rectangular columns by assuming D equal to 0.8 H. In fact, if you have a column, the D or the effective length is not a one single value. D varies with or will be different for each load combination because this depends on the location or the location of the load combination point in the interaction diagram. This will be very complex. This is not easy. That's why the code need to use a simple assumption by assuming D equal to 0.8 H when you would like to calculate the shear strength for a rectangular columns. Also, in fact, B, C, or D, nothing new in these options. If we look here, if you have a circular section, we can assume that the if you have D equal to 0.8 times the diameter for circular sections, D equal to 0.8 H for rectangular sections, B sub W or the width that you will use to compute the one-way shear equal to the diameter for solid circular sections, or will be equal to the twice of wall thickness for hollow circular sections. This is shown here. As you can see, B sub W equal to double the thickness of the hollow section. Here, B sub W equal to the D diameter. Effective depth of circular section will be 0.8 of the total depth, and so on. This is what I need to discuss here. Okay, also in ACI 318.25, the code now states clearly that the scope of chapter 22 includes composite concrete members, composite steel or composite structural steel concrete beams are not covered in code. If you'd like to design a composite structural steel concrete member, you have to go to AISC 360. So ACI code covers only the composite action between, for example, a concrete beam and a topping slab. Here we have a composite action, but again, between concrete member and another concrete member. So let's say a precast beam with a topping slab. This case is covered by ACI in chapter 22, but if you have a composite steel concrete beams, for example, here we have I section as a steel, and here we have a topping topping slab. This is beyond the scope of the ACI code now, and you have to go to 360, AISC 360. Okay, here, by the way, I believe these equations in British units, not metric units. In ACI 318.25, there is no change for the main equations of one-way shear. These one-way shear equations are the same or are similar to equations in ACI 19. But we have another major changes I will discuss in next couple of slides. Before going through that, I would like to highlight why ACI changed the one-way shear equations in ACI 318.19. If you look into ACI 318.14, you will find another equations. So what happened, in fact, that the ACI 318.19 changed the main equations for one-way shear. In fact, this was based on a lot of experiments, tests for many samples. So as per ACI 445 for shear and torsion, here we have the number of samples that the ACI used to test the previous equations for one-way shear. We have here more than 700 samples for reinforced concrete sections without minimum shear reinforcement. We have 170 samples with minimum shear reinforcement, 200 something pre-stressed concrete section or beams without minimum shear reinforcement, also pre-stressed with minimum shear reinforcement. So here we have samples, more than 1,000 samples ACI tested to check the adequacy of one-way shear equations. So what they found, in fact, these results will be very interesting for all structural engineers to understand why ACI changed the equations in ACI 318.19. If you look here, this equation has been used in ACI 318.14. This is by metric unit or metric unit, okay? In fact, these samples were tested without minimum shear reinforcement. So here we don't have a minimum shear reinforcement. If you look here, any point below this line, this means non-conservative result. I will not say unsafe, I will say non-conservative. By the way, not satisfied. So all samples below this line, in fact, were or failed on a strength less than the expected strength as per this equation. Why? The main reason is because of the size effect factor. If you look to this equation, there is no size effect factor in this equation. That's why for sections with depth less than 250, we have very nice results here. But for sections with depth more than 250, we have some or a lot, I will not say some, a lot of samples failed on a shear less than the shear calculated by this equation. So in fact, we have an issue. We have a problem. Okay. Again, this equation has been used for a long time in ACI 2014. Again, we have the same issue. As you can see, this equation called detailed equation. This is simplified equation. The simplified equation in blue points and detailed equation in orange points. As you can see, both of them failed, or all samples, or I will say most of the samples calculated using this equation failed also on a shear less than the expected or less than the calculated shear using this equation. So still we have issue. As you can see also, for samples with depth less than 250 millimeter, we have in fact nice behavior, nice test results. Most of the samples are above this line, so we can call these samples as a successful or conservative result. Okay, when ACI introduced the size factor, as you can see here, a lot of samples now shifted above. As you can see here, this is very important. Again, here the shear reinforcement is less than the minimum shear reinforcement. So again, what the ACI did, the ACI only added a factor, a new factor to this equation called size effect factor. As you can see here, as we increase the size more than 250, a lot of samples failed, and as we can see below the line of v test to vn equal to 1. But when the ACI added a size factor to this equation, here we have a very nice results. As you can see here, in this area, when the steer ratio is below a certain level, we have some, or I will say, good portion of the samples also failed, and or I will say failed on a shear value less than the expected one by this equation. So from here, they start to focus on the effect of the flexural reinforcement, I will say, because I will say something here. In many tests have been done in the past, the ACI team, I will say, we're providing a high ratio of flexural reinforcement to push the samples to fail on shear, not on a flexure. That's why they didn't notice the effect of the main flexural reinforcement on the calculated shear capacity. But from here, as you can see, if the steer ratio is less than or lesser than a specific ratio, here we have many samples failed and didn't satisfy the minimum strength. As you can see here, when we provide the minimum shear reinforcement, the results also improved a lot, and we have now few samples only failed, and I believe that ACI always accept a percentage of samples that they will fail and they will not reach the target or the expected calculated capacity. That's why, as you can see here, when we provide the minimum shear reinforcement, the capacity of the sections have been improved a lot, in fact. Okay, so As per ACI 1819, we have three equations. If I would like to use equation A or B, any of them, I have to provide minimum shear reinforcement. So if you, for example, you would like to calculate the one-way shear capacity of the raft foundation, and you don't provide a minimum shear reinforcement, you cannot use, for example, equation A or B. You have to go to equation C directly. I am talking about 31819, version 19 of the code. But for example, if you have a beams, the beams typically contain the minimum shear reinforcement. That's why we can use equation A or B. Okay, how to decide in which cases I have to use A or B? In fact, you can calculate the VC one time from the equation A and another time from equation B, and you can take the largest value. But here I would like to show you this graph from ACI University webinar. If you would like to take the benefit from equation B, the minimum steer ratio shall be more than 1.5%. As you can see, because in this equation here we can see the steer ratio effect. So if you would like to feel or to take the benefit from the additional strength using equation B, the minimum steer ratio in the section shall not be less than 1.5%. In fact, 1.5% is a high percent of reinforcement, especially for beams or for slabs. So practically we are using always equation A, but again you can use B. If you'd like to use B, you have to provide a lot of reinforcement to improve your shear capacity. Beyond the 1.5%, as you can see, equation B will always be less than equation A. Okay, now in ACI 31825, here I will go back for this. In fact, this equation, I will say, made a lot of issues to the practice engineer in the market, and we have provided a lot of reinforcement shear links. In one of the projects, I remember that we have provided more than 700 ton of reinforcement to provide the minimum shear reinforcement for a raft of the tower. That tower was around 100 floors in the sky. At that time, the code or the used code for that project is 31819, and if you would like to use this equation, we have to provide minimum shear reinforcement. Otherwise, we have to use equation C, which will result in a very low shear capacity. So at that time, we have decided to use a minimum shear reinforcement. In fact, in that project, as per the quantity engineer, he told me that the amount of steel was 700 ton only as a shear length. But in ACI 31825, there are a lot of major changes in such situation. I will say that the code members released that this equation resulted in a very low shear capacity. That's why they provided a minimum threshold. So if you calculate the shear capacity from this equation and you get a number, or you get a specific number, as per ACI 31825, now there is a minimum threshold. You can select this, or you can calculate the minimum value, and typically this minimum value can exceed the value calculated by equation C. I will give an example. By the way, if you would like to use the minimum threshold or minimum value of VC, you have to know that we have exceptions. We cannot use the minimum value for elements subjected to a net axial tension. A net axial tension, this means that the tension is more than the compression force. Or for special moment resisting frame, you cannot use this minimum uh, uh, threshold. Also, for I will say I will go back here for I will show you. Wait, I will show you this from the code. In fact, this is code 31825, chapter 13 for the foundations. If you look here, we have a new major change in the code, as you can see. For a shallow foundation members continuously supported by a soil and designed based on the assumption of rigid behavior of the shallow member, A and B shall be permitted. As you can see now, the code permits you to use this equation also without the size effect factor. But before the code 25, or at the time of using 318.19, we have to use equation C. Equation C required a lot of reinforcement and required to increase the depth of the foundation. But now I believe ACI members, they released, or they recognized that that equation is not suitable and will result or resulted in a lot of loss in the cost of the projects. As you can see here, for one-way shear strength of shallow foundation, you can use this equation. This equation same like equation of ACI 318.14, and also for two-way shear strength, the size factor shall be taken equal to 1. Now you can get a very higher shear strength when compared to ACI 318.19. Also, the same thing for the piles. I will show you here also. For the retaining walls also, you can use this equation. This equation, in fact, shall be used for the in-plane shear, but for out-of-plane shear, yes, for the basement walls, as you can see, it shall be permitted to calculate the one-way shear strength of concrete using this. This also will help you to get a very nice shear capacity for your basement wall. I remember that a lot of shear links were provided in the past to run away from this equation. So in the ACI 318.19, if I would like to use equation A, I have to provide minimum shear reinforcement. But now in ACI 318.25, you can use it directly. But again, this is for in-plan shear strength. For loads other than out-of-plan lateral earth pressure, basement walls shall satisfy applicable provision of Chapter 11. Also for piles, we have a good change in the code. I will show you. Yes, this is for piles. As you can see, here for pile caps with the piles spaced at 4 pile diameters or less, and for mat foundations while piles spaced at 5 pile diameter or less, A and B shall be permitted. You can use this equation for 5C, and also the size factor equal to 1. In fact, this is very serious provision that all engineers must recognize. Why? In fact, in one of my projects, I remember that the raft thickness was 4 meter. If you would like to calculate the size factor for the 4 meter, it will equal to efficiency of 2 meter only. Yeah, for example, if you calculate the shear strength of the 4 meter, because of the size effect factor, the shear strength will drop around 50% or more. That's why in ACI 318.25 and in a certain conditions, and I believe in most of our projects, the spacing or the space, the piles are spaced at 4 pile diameters. I believe in the practice we are trying to keep the spacing between 2.5 to 3 diameter of the piles diameters. That's why we can use this equation, and definitely this will help you to get a reasonable sections and reasonable reinforcement. Okay, I will give you an example to feel the numbers. For this section, assume that this is yield strength, this is the cover, effective depth, and also if you need to calculate the size effect factor for this section as per ACI code will be 0.415, and also rho W is the steer ratio is around 0.0097, and here we don't have axial tension. If you calculate the shear capacity of this section as per code 2014, you will get 2850 kilonewton. But if you need to calculate the same shear capacity for the same section, I mean, as per ACI 19, you have to know that we have three equations. If you provide the AV minimum or the minimum shear lengths, equation A will result 2849. Yeah, so if you provide the minimum shear reinforcement, the result will be similar to ACI 2014. Okay, if you would like to use the second equation with this, I will show you the second equation. I mean this by second equation with the steer ratio. The shear strength will be 2359, still nice but less than A, so I can use A directly. Again, the steer ratio is less than 1.5%, that's why equation B didn't result in a higher value. But if you don't provide the minimum shear lengths in your beam or in your, by the way, this section can be for a raft or pile cap, by the way, not a beam. As you can see, equation C results in a shear capacity 980 kilonewton. This is very interesting. This is very low value. So if you don't need to provide minimum shear lengths, you have to assume that the shear capacity of this section is only 980 kilonewton. As you can see, the same section in ACI 2014 is 2849. This is really interesting. In ACI 318.25, again, the code is trying to help by providing a minimum threshold. This minimum will result in 1,400 kilonewtons. So, as per ACI 318.25, if you don't need to provide a shear length and you would like to use equation C, no need to assume the strength below this value or less than this value, so you can take this value even without providing a minimum shear length. Okay, in fact, steer ratio here, as you can see here, this provision has been revised a little bit. Steer ratio, typically or practically, we are taking the flexural reinforcement, tension reinforcement. Also extra reinforcement if you have, you can use in this value. Also ACI 318.25 now recommends, I believe, using steel fiber reinforced concrete. Using steel fiber reinforced concrete can result in a higher shear strength. In fact, also, as I said before, we have some minor changes, same like for two-way member before. Now they added a shear, as you can see, shear. So don't think that if you see this bar that we have always a major change or major changes. No, sometimes we have only minor things. For the openings or for the opening effect on the bunching or two-way shear capacity, no changes in ACI 2025. In fact, almost the same. Also for two-way shear strength equations, we have the same equations, no major changes. Also here we have some comment or some I will say important commentary added in 318.25. The commentary states that the requirements of 22.9 were developed based on monotonic testing and may be unconservative for interfaces that are part of seismic force resisting system and experience strength degradation due to force and displacement reversals. Uh, this person provides design guidance for interfaces subject to cyclic loading that could cause sliding. In fact, this is related to shear friction calculations. In ACI code, we have chapter or we have section 22.9 for shear friction calculations. Shear friction calculations can be used for the cold joints, for the diaphragm design, for the column floor joints, cold joints, I mean construction joints. So there are a lot of cases that we can use. Also in corbels design, we can use the shear friction calculations. The main idea here that the code says now that the shear friction calculations provided in the code were developed based on the monotonic testing. If you have cycling loading, you have to expect a degradation in the strength, so you have to expect a lower shear friction capacity of a specific section. I will show you here this sample. In fact, here we have a load, here we have a load, and here, as you can see, we have some like a gap here. We have a gap here. When we apply a loads at the two ends, now the failure or the expected failure will be along this line. If the slip will occur, those members will be subjected to a high tension force. This mechanism called shear friction mechanism. So even you have here, even if you are applying a shear force on those bars, you have to know that the forces developed inside these bars are a tension, not as a shear. So you have always to satisfy the development length and tension on each side of the expected shear failure or shear plan failure. You can refer to these ACI structural journals. Again, here, if we need to summarize that for the shear friction, the code developed the equations of shear friction calculations based on monotonic loading. For reversal loading, same like seismic, the expected shear capacity or the expected capacity will be less than the code expectation. Here we have different degree of roughnesses used for the shear friction calculations. If you would like to read about that, you can read or you can go for this reference, ACI technical guideline. And also in ACI 318.25 now, the code added this term to the shear friction equation. This term is for the compression. If you have a permanent compression on the shear plan, so the code permits you now to increase the shear or shear friction capacity because of this permanent tension, because of this permanent compression. This is very important. Also here I need to highlight that if you have, I will draw that. If you have a footing, let's say, and here we have a column. Typically here we have a construction joint. Okay, here also we have reinforcement. At the construction joint, you have to calculate the required reinforcement. For example, we have a moment and we have axial force and moment. We have to calculate the required flexural reinforcement for at this connection, and also here we have, for example, lateral load. We have to calculate the shear friction reinforcement. Shear friction reinforcement is not additive to the flexural reinforcement. No, as per the code, you would basically calculate the reinforcement required for shear friction and then calculate the reinforcement required for flexure and use the larger one. A lot of engineers, they are thinking that the shear frictions reinforcement always additive. No. But again, here we are talking about flexure. If you have a tension, this is different issue. Tension reinforcement always additive. Uh, Again, here also this an ultimate to take the effect of the compression. If you have, for example, if we have here assume the crack and shear plan, and here we have a compression, and here we have a compression. This compression is permanent. This will improve the shear friction capacity at this shear plan. Also, you have to know when you calculate the shear friction, or when you provide or need to check the shear friction at a specific section or shear plan, you have to know that we have upper limit on the shear capacity. If you exceed these limits, you have to increase the section size or the grade of the concrete. As I said before, if you, for example, let's assume that I have a section in the raft, and here we have a construction joint, okay, and here we have a bars passing the construction joint. When you would like to perform here the shear friction calculation, you have to make sure that the reinforcement will develop the development length on the both sides of the shear plan, because again, if we have a bars here and we have out of plan shear, this shear will cause a tension inside the bars. That's why we must develop these bars in tension. Also in ACI 318.25 we have additional provision for the shear friction reinforcement used for example, a composite section. That's why if you have a topping slab and you have a beam, or sometimes precast beams, or precast beam, let's say, you can provide the shear friction capacity across this cold joint using U-shape reinforcement. U-shape reinforcement. But here you have to provide the development length, and again you have here another requirement, same like the spacing across the cross section, and also the spacing along the beam length. And here you have minimum diameter. You cannot use diameter less than 10 millimeter. So I believe that this provision can be useful for engineers, but again, take care, these transverse reinforcements cannot be used for the torsion. If you have a torsion, the stirrup must be enclosed. It cannot be only as a U shape, because it shall be permitted to consider inverted U bars extended into composite topping slabs. So here we have a U bars. U bars cannot be used to resist the torsion. If you have a torsion, the stirrup or the external stirrups must be closed. Again here, if assume that this is a plan in the raft, and here you have a construction joint, you have to perform the shear friction calculations based on the maximum shear force with the corresponding tension, if you have a tension, and also another time for the maximum tension with the corresponding shear. And you have to provide the reinforcement as per the maximum effect. Also, don't forget that when you calculate the shear friction reinforcement, you have to assume yield strength of the reinforcement as a 420 megapascal. You cannot use more than this value. Also, shear friction reinforcement must be distributed along the shear plan. Thank you, engineers. I hope that this was useful for you, and I hope that we can discuss other topics in the future.